let's look at, for example, something similar to number 3, and we'll do actually that example I just suggested. So we'll do number 3. And let's do f of g of negative 5. So this is called function composition. Function composition says that we work in, then out. So the first thing we're going to do is actually find g of negative 5. So g of negative 5 is 2 times negative 5 minus 1. So you get negative 10 minus 1, or negative 11. So f of g of negative 5 is really the same as f of negative 11. F of negative 11 is then negative 11 squared minus negative 11 plus 1. Order of operations, say we square to start. So you have 121 minus a minus turns to a positive. So 121 plus 11 plus 1 is 133. Okay, down in problem set number 4, we have a piecewise. A piecewise function are those graphs that kind of look like all the different graphs that like don't match up, and they have some holes and they have jumps and they're different shapes curves. So if you look at number 4, you have a quadratic and a linear function. And what we did was we found them at f of 5. And here we're going to talk a lot about continuity. Continuity is basically where you have a piecewise function, like example number 4. And in order to determine if it's continuous, we would need to see if the value at 0 is the same. So if I ask you in number 4 to find f of 0, would you put 0 into the top function or the bottom? For number 4. Good? Exactly. So the top one is the actual function that gets the 0. So we plug f of 0 in to the top function. So the true value of f of 0 is 0 squared minus 3, or negative 3. To determine if it's continuous, we would find f of 0 for the bottom function. So you just plug 0 in, and you have 2 times 0 plus 1. So 2 times 0 is 0, so you get 1. Is this function going to meet up at the same spot? No. So this is not continuous, and that's something that we're going to talk a lot about in chapter 1. Continuity of a function. Next page. All right, domain and range. I just actually spent last period with advanced algebra 2 talking about domain and range. So domain and range represent the x and y values of an ordered pair. We have lots of different notation that we can use to describe domains and ranges. So that's everything kind of at the top. It goes through all the notations. You will find in here, we use a lot of interval notation. So if we're using interval notation, you want to remember that a parenthesis means it gets infinitely close but does not include. And a bracket means that it does include it. So the bracket is inclusive, the parenthesis is infinitely close, but not quite there. So if you look down at the examples they gave you, one is considered a polynomial function. A polynomial function always has domain and range, all reals. So all polynomials have a, well, not range, sorry, because that's an even, but domains that are all reals. Number two, x does not equal -6. That's called a vertical asymptote. So vertical asymptotes can occur. So number two, when you would graph that, basically at x equals 6, what? Oh, you know what these are? I hope so. This is a review. I'm not teaching you new stuff. Not yet. I was just making sure everybody's on the same page. So you'll have that vertical asymptote at 6. And then similarly in 3, you would factor it, make sure nothing cancels, so you have no room of movable discontinuities. And you have 2 more vertical asymptotes. Square roots domains always come from what's underneath the square root and then greater than or equal to. Cube roots are always all real. Okay. So there'll be a couple problems in letter B on domain and range. I'll have you do something similar to that. All right, letter C is all about what do these graphs look like. So what I did is give you examples of parent functions. A parent function is a unchanged graph. So the parent function is the graph that is not changed. So in this case, the parent function is y equals x. That is your linear parent function. It goes through the origin, has a slope of 1, 1. Parent function for x squared goes through the vertex. It also has a slope of 1 and no transformations up or down. All right, so there's not a lot to do with that. These are just really helpful graphs you're going to want to have easily accessible. Letter D. Here's where we have to start really remembering the important even and odd. So in order to determine if a function is even or odd, you're going to plug in negative x. So to find even or odd, you plug in negative x to the function. So if when you plug in negative x, you get back f of x, then this is even. If when you plug in negative x, you can take a negative 1 out, meaning you can pull out a GCF of negative 1, and you get negative 1 f of x, then this is odd. If I do not get either of those two cases, then it is neither. You don't get original or negative 1, then it is neither. Do we want to practice plugging in a negative x, or are we okay? Sure. I'll even be nice and do one out of the packet you're going to work on. Just because I don't want to make up a problem that may not work out nicely. Alright, so let's look at f of negative x. And our original function, f of x, is equal to 2x squared minus 4x. And what we're going to do is put negative x into this. So you have 2 negative x squared minus 4 negative x. A negative times a negative is always a positive. If you plug a negative x into the square, it becomes a positive. So you get 2x squared. And a negative is a positive for x. Is that the original function? Can I take a negative 1 out and get, nope. So this is the case of neither. Oftentimes, if you have mixed exponents, meaning an even exponent and an odd exponent, it's going to be neither. As long as it's a polynomial. That doesn't stand true once you get into more complicated functions, but that stands true for polynomial. Sorry. The kiddos at home are actually kind of listening live. So that's why I have to be unmuted. But it's starting to echo, so I fix my other computer. Questions at all on that? Okay, then let's move on to letter E. Alright, so I love this page in letter E. This page is so helpful for helping you understand how graphs move. So if you have a positive a value being added after the parent function, then it moves your graph up. If you have a negative a value after the parent function, it moves your graph down. So in this case, that example parent function is x squared. What we want to do, let me see if I can upload a photo. Big photo. All right. So what we're going to do is, this is a quadratic. We can actually come up with a reasonable estimate as to what these transformations might be. So for that first one, what do you think a reasonable estimate would be for that transformation? Like +2? So if the parent function is x squared, then this graph might represent x squared +2. I wonder if it's going to let me write the right here. It does not. The second one, that graph is transformed down. So that would be like x squared -2. Here, you see that the a value being inside moves it to the left. So that graph is moved to the left. How many units to the left might we think it's moved, Frederick? Yeah. So that inside means it has to go inside the squared part of our problem. So it becomes x minus, and now remember the formula for this is a little tricky, right? So So it becomes x minus a minus, and you see how even here it shows a positive, moves it to a left? So it would be plus 2. Moving it to the right, again, is the opposite. It's x minus. So that might be x minus 2 squared. If something is stretched, it becomes narrow. It's like lengthening it. So I say like you guys get stretched out, like when you have a growth spurt. So all that really changes is your height. Well, a graph that's stretched out is similar. What's changing is its height. So this graph might look like 2x squared. So the a value goes in front of the parent function. A graph that is shrunk, another word for that is compressed, it gets wider. So it'd be like taking you as you are now and making you wider and shorter. Your weight's not changing. All that's happening is you're getting smushed to the sides. A compression is a value between 0 and 1, meaning it is a fractional number. So maybe this is like 2/3 x squared. A horizontal compression has the same effect as a vertical stretch, but now it's on the inside. So that would look like 2x squared. Similarly, a compression would be a fraction on the inside. So it'd be 2/3 x squared. And apparently I didn't take a picture of the bottom. But if it's reflected across x, the negative is outside. If it's reflected across y, the negative is inside. I don't know how that let me finish. We only have like a few more letters left, and then we'll go outside. Just because they're listening live back in at home. Yeah, I mean, I'm just learning how to do it. I found it like on Friday afternoon, and I was like, I think this is gonna work. Because my son goes to Peters, and he has to be online at certain times for live lessons. And they use this, and I was like, that's awesome. So then I like started to play with it. I like that like I can be on here and I like have it testing on there, and then I'm recording my screen on my laptop, but still presenting on my, and I can like write with my pen on it. I was really happy after it. They can hear me. That's why. What? Yeah. Yeah. 2 of them were. No. All right, so letter F is all about factoring. We're going to factor a lot. If you don't like to factor, I'm sorry.
Attention all gym classes, please report during your period Mr. Hamalka's classes to the library classroom and Mrs. Spiegel's classes to the community room. Again, during your gym class, report to either the library classroom for Mr. Hamalka or the community room for Mrs. Spiegel.
Okay. We are going to factor a lot. Next week, we'll learn about something called Pascal's triangle. It's going to help you factor and FOIL. So up at the top of that page, I give you some of the formulas for certain factorizations, like perfect squares, sum of cubes, difference of cubes. There's not a whole lot except for doing problems with you to help you on this. So if you get stuck working on this letter in your packet, I'll gladly do one of the problems with you to help you. But yeah. And then the very next page, linear, is I hope I know you know how to slope. I will tell you that this year you are not going to call slope slope. This year slope is going to go by a new name, and our new name for slope is going to be rate of change. You are going to hear me say rate of change probably once a day. Calculus is all about slope. A derivative is the slope of the previous function. But instead of calling it slope, we talk about rate of change. So, you are going to get super comfortable with delta y over delta x. We are going to talk about the change in a function. You're going to hear me say slope of the secant. Sorry, I moved on the line turning. So we have slope of the secant. This page is going to be really fun for you because basically you're going to be going from one form to the other, and it's very easy. I assume you'll probably do really well with letter G because you're going to be finding slope and then using one formula to get to the other. I really like point slope form, so if you don't or haven't used it a lot, you will a ton this year. We're going to do a lot with y minus y1 equals m x minus x1. So again, the y1 and the x1 come from your point, and then you're going to be plugging that point in. We will leave it in this form a lot. This is an acceptable form. And again, in case he's taught you in physics, did he ever talk about Did he ever talk about something called a tangent? In physics, you guys talk about tangents? So this equation here is the equation of a tangent line. So when an object is tangent in physics, it's actually coming from this equation here. And in calculus, you're going to learn how to find that equation. Yeah, so when we talk about trig in like 2 or 3 days, you're going to learn that the tangent in this is the same as the tangent from trig. And if you recall the unit circle, you have to see you're taking off on a tangent. If you recall the unit circle, I can actually use the circle on here. Because I haven't played with this yet. This is like fun. That was a nice little fun find for me. On the unit circle, this would be a tangent line. 2, so here's your point. If you go from that point, this represents your angle, theta. So this line represents tan theta. But what is tangent in terms of our other 2 most important trig functions? Tangent is really what? No. Sine over cosine? Okay. The sine is which coordinate? Where do you get sine from? Is it x or y? Oh, it's y. And what's cosine? What does this look like? What tool did I use to draw it? Line. That's not a question, kiddos. I used the line tool. What if I just put this little symbol right there and that little symbol right there? A tangent, aka tangent line, is really what you were finding all around the unit circle. Boom. Because what were you finding the change in? You were finding the change, that's why I use that color, from this point here. What's this point right here in the unit circle? Oh man. What's the coordinates of that point? 1, 0 to this point up here, which we don't know what it is. We just know that it is cosine theta, sine theta. So what is slope? Change in y over change in x. So it was the sine of theta minus 0 over the cosine of theta minus 1. And that, my dears, is how you got tangent. I'm sorry if but see, that's why I love calculus. See, like when you just saw that, oh my gosh, that makes sense. Like that is what you're going to say every day here. You're going to find something you've been doing in mathematics for a long time that now makes sense. And you know what we're going to do on the next page? So you're going to love it so much. Quadratic formula is the last letter of today's review. So, we're going to solve quadratics mostly for these types of problems. I assume when you learned the quadratic formula, you learned that it was negative b divided by 2a. You learned this part first. What does that negative b divided by 2a represent? What's this actually right now sitting as we are? That is the equation of the, oh dear me, I'm going to cry. It's not a solution. It's something on the graph of a quadratic. Yeah, well, he said it. What is it? Not the x-intercept, I lied, he didn't say it. Not the y-intercept. I know, I thought you said something else. Does AOS mean? Axis of symmetry. Negative b over 2a represents the axis of symmetry. It represents the part of the quadratic where it is cut in half. The second part to that formula is a positive and a negative, right? And then you are adding or subtracting the discriminant this piece of information here, this represents the distance from the AOS. And then the plus or the minus is the going in both directions. So you're adding or subtracting that piece to this side, adding or subtracting that piece to this side. And that is how you get the roots. So the quadratic formula, there you go. What is another name for the roots? Zeros, or you said x-intercepts. And I will leave you with that. Mask break.